My name is Sophia, and this is my Lab 4 about circuits. The purpose of this experiment was to predict the behavior of circuits containing resistors in series and in parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. Some fundamental principles that are important to understand are the conservation of energy and charge, the RC lab formula, Ohm's law, capacitance, resistance for circuits in series and parallel, and Kirchhoff's circuit laws, which are the loop rule and the node rule. The assumptions made for this experiment are that the resistance of the wires and ammeters are negligible, and EMF equals delta V cap plus delta V resistor. The results of the experiment were that the predicted and experimental values for current and voltage are the same, and in an RC circuit, the magnitude of current is time dependent based on exponential equations. So for this experiment, the system was the circuit and the surroundings were everything else. The initial conditions were that we used two 1.5 volt batteries and two resistors of 47 ohms and 100 ohms. First, we created a circuit with two ammeters, and we predicted that the current in the first ammeter would equal the current in the second ammeter because of the node rule, and that the total resistance would be 147 ohms. Therefore, the total current would be 0.2 amps. The actual current was just that, and if we replaced one ammeter with a voltmeter, we got that the delta V was equal to 3 volts and the current was 0 amps. Then we closed the circuit and measured the potential difference across each segment, and there you can see the measurements for each of those locations, and we concluded that the delta V total was equal to 0, which follows the loop rule, and the current remained the same at 0.2 amps because the voltmeter has high resistance, so no current flows through it, and the path of the current in the circuit remains unaltered. Here is the approximate graph of potential. So you can see that at location C, it decreases, remains the same in between D and E, and then decreases again in between D and F, and there is no overall change. Then we connected an ammeter in parallel with the 100 ohm resistor. The current was equal to 0.06 amps. Because less current comes in contact with the 100 ohm resistor because it splits at the node, and the ammeter has no resistance, so the overall resistance of this portion of the circuit will decrease, which increases the overall current. The resistance of the 47 ohm resistor was equal to 48 ohms, of the 100 ohm resistor was 102 ohms, and of the wire and ammeter there was 0 resistance, and the values are slightly higher than expected because the ammeter had low precision. Then we connected a 9-volt battery, 10-ohm light bulb, and 200 millifarad capacitor in series. The light bulb started out bright, then dimmed over time, and eventually went out, and that was the charging of the capacitor, and the current decreased from maximum amount to 0. Then we disconnected the battery and connected the capacitor directly to the light bulb. Then the light bulb again lit up and then dimmed over time and eventually went out, and that was the discharging of the capacitor. Then we repeated that with a 20-ohm light bulb, and we timed how long it took for the charging and discharging of the capacitor. For the 10 ohm light bulb, it took 10.5 seconds to charge and 12.4 to discharge. For the 20 ohm light bulb, it took 17.3 seconds to charge and 22.3 seconds to discharge. Then we took several readings for the potential difference across the capacitor as a function of time over 20 seconds using a 30 ohm light bulb. So we plotted those results, and as you can see, the equation for the line best fit is right here. Then using that equation, we can find the slope of that line and calculate our experimental RC, which was equal to 6.02 seconds, so we can assume it was just equal to about 6 seconds. And the expected RC is equal to resistance times capacitance, which was also 6 seconds, so they were equal. Answering a few discussion questions. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Essentially, the ammeter would have likely had a small amount of resistance instead of 0, so the current reading would have been smaller because more resistance in the current results in less current. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? The ideal model would predict that the capacitor would reach full charge immediately because there would be no resistor to slow down the current and remove potential difference. Then how quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? In real life, this prediction would not happen because the wires would likely have some small amount of resistance, so the capacitor would charge slower than in the ideal model. The only source of error was likely human error while stopping the stopwatch because we used a computer model.